Hello, everyone. The purpose of this video is to step you through some of the essential steps that you would need in order to complete the Brian problem. So with that, let's go ahead and get started. You can find the Brian problem description located in this week's materials if you're following along. And so I just opened up that document. And what we're going to do is template this out. The idea behind the Brian problem is, number one, to understand a little bit more about how to scope and understand sort of these word problems and how can we make sense out of them. And in that context, to really step you through what I like to call backwards design. Backwards design essentially means for us that we will be working from a goal to identify what type of analysis we need, and then working backwards from there to isolate out a data source that can best help us out. So with that, let's go ahead and get started. So this was a real, I'll call it real world problem, if you will. It was from a student from quite a number of years ago, working on a project somewhere beyond the university here. And this was a snippet of the actual email that you're looking at on the screen. And his name was Brian and was interested. And we read through that. My project is to find best places to restore prairie habitat using slope and direction. Most prairies around here are found on steep slopes of the bluffs and facing the southwest. I made a tin from a DEM to get the 3D image, but I need to run a buffer and use 2 geoprocessing tools. And Chad mentioned that Brian might need a shapefile to do this. And so Brian converted the tin to features, hoping that there would be a layer of slope. Unfortunately, my new layer had no attribute data. Chad wasn't sure what I was doing. So could you help me with the situation, with the problem? So when we're looking at this problem, the first thing I'd like for you to think about is, what's our goal? So go ahead and pause the recording and think about the goal here. That's going to drive everything. The Brian problem is an excellent example of a final project for this class. That's why these word problems and all the crazy language and whatnot used in here doesn't mean that it's necessarily necessary. In other words, what are we trying to really isolate out of here? So as we'll soon discover, we have a goal, but the data set is really pretty interesting and easy to acquire. So oftentimes we do not need a lot of data to make a really cool project. So with that, go ahead and pause the recording and think carefully about what is the goal here and what do we need in this information and what is sort of redundant that we do not need. So I'll just pause for a second, let you think about that. Okay, so maybe you paused for that, maybe you didn't. But if you think about our goal, the long and short of it is, if we look at that, now Brian's working to find ideal prairie habitat to restore. So if we look at our goal in our backwards design principles, I like to start on the right-hand side and work backwards. It's part of our backwards design. We'll call it backwards design. What this enables us to do is to identify the problem first and then work backwards to isolate the parent data source. For some reason, that's not focusing for me. There we go, backwards design. So we have our goal, identify prairie habitat areas. Next, let's take a look and identify in here, what are some things that we really want to keep and some things that we do not want to keep and are just sort of unnecessary fluff, as I call it. So ask yourself that question, pause the recording, see if you can identify some critical things in knowing what you know so far about data and how we could make this run. All right, so if you paused or if you didn't again, let's go ahead and take a look at that. So in the dialogue stream here, we notice right away, we can identify our goal, and we're seeing some things on slope and direction right here, and that is helpful. And most prairies around here are found on steep slopes of bluffs facing the southwest. So right off the bat, we know that we do not need a tin in order to make this happen. Those of us who are familiar with elevation sources, you probably already are thinking about this. So we certainly do not need a tin, nor do we need a 3D image, whatever that refers to. And certainly, you know, my take on buffers. When I don't use a buffer, just kidding. I think buffers have their place, but too often they are used when we do not need them. And so pretty much everything from this sentence down is really, we don't need that. So pretty much all of our information is found in the second sentence and our third sentence. So we know right here that we have aspect, or the direction, in other words, the orientation of the land, something facing southwest. And then we also have information here about steep slopes. And that gives us essentially what we need to solve this problem. Well, let's go ahead and build this out. Knowing our goal, identify prairie habitat areas. Okay. So given the parameters that Brian spelled out for us, let's go ahead and draw some boxes. Brian mentioned southwest facing slopes. So some southwest facing slopes. We know that was one of them. One of our criteria, when we think of data sources, we think of them as variables, meaning data layers, and then criteria. In other words, those are the metrics that define our analysis. So oftentimes they are numbers, in our case, working with rasters, that define an ideal, I'll call it ideal areas or ideal values from our original rasters. So we think of this as the parsed down area or the subsetted information. This week we'll be working more with subsetting. But right now we know that we have southwest facing land. That was one variable, or I'm sorry, criteria that Brian left for us. So we're thinking of this kind of this block right here as our criteria, you know, the criteria for success for our project. Okay, the other one that Brian mentioned was a steep slope. You know, and the question for us, to move this down here a bit, you might be thinking right now, what does steep mean? That's a key question for us to identify. And when we're not sure what this is, so for some of you, if you move into capstone, it's important to define what this is. And if we're not sure what it is, well, what can we do to define that so that we have a greater sense of validity of in our methodology? And I like to encourage people to turn to, you know, your literature, what's out there, what have subject matter experts noted on that for what is steep, you know, what is a steep slope, you know, for prairie. And we don't really know what that is right now. We're kind of guessing on this just for the sake of the exercise, but I'm going to say 26 to 50 degrees. There's degrees and percent. We're going to say degrees, so 26 to 50 degrees for steep slope. So we don't know that for sure, but it's a best guess. But if this were real deal for you, what I would recommend is defining this with literature to know what steep means. That way you'll be able to defend that more successfully. Okay, so we have right now the two criteria that Brian noted in the document. steep slopes, and facing southwest. All right, so now the question for us right here, right now, we're thinking about, okay, if these are really some of the final criteria that I need, where can I obtain southwest facing land? Again, backward design. And to that end, when we're thinking about aspect or the orientation of southwest facing land, a lot of this is through experience too. So the more you get an opportunity to get into working with different data layers and whatnot, you'll know what layers can produce, our final criteria here that we're into. So I'm just trying to introduce this for you in an experiential way to get you some new insight. All right. So if you're thinking about where can I obtain southwest facing land, you might be thinking about some prior experiences. So we're kind of coming back here to data, not necessarily the parent data. So we're calling this column here really that of our data layers, or a subsetted data layer, as we're soon going to find out. But you might be thinking already, an aspect raster. An aspect raster could be derived, or we'll call it subsetted, to pull out southwest facing areas of land. So we're going to call this, we can subset or grid query. We're going to call this one subsetting, or when I say grid query, raster query, using maybe Raster Calculator or something like that. Querying, almost like you do with vector layers, except we're going to be querying numbers, values. Remember, because numbers have meaning, the values have meaning. So this is called subsetting or a grid query, whereby we have a raster layer. We have a raster data layer, and then we subset out values of that raster layer that are of southwest facing land. And we're going to show you what this is all about here in just a minute. So I'm showing you this in advance so that you can sort of prepare yourself for once we get into the actual work along here. All right. Same thing down here with our degrees and slope. Again, we're working with our raster data set. Now the question for you is, where can I obtain degrees of steep slope as a final criterion for analysis? And you might be saying to yourself, well, if I had a slope raster, you could do that. So there we go. We have a raster right here. So in thinking a little bit further now, kind of the backwards design principle. The question for you is, where can I obtain an aspect raster? Where can I obtain a slope raster? So I'll give you a minute to think about that. Where could I obtain a data source that could give me both aspect and slope? So the question or the answer to that is fairly simple, which is good. If we had one DEM, a digital elevation model, or we could use LiDAR too, that's fine, but something with elevation. We have one data layer. One data layer is all we need in order to solve the Brian problem, at least given the parameters that Brian gave us. So over here in our general flow, if you will, here we have our parent our parent data source right here. That's all we need. That's our parent data source. Then all we are doing is starting to derive data from the DEM all the way over through our goal. So what's happening is we are deriving data as we move across left to right. We're deriving aspect, we're deriving slope. From our two rasters, we're sort of deriving new final criteria, but more I call it, well, yeah, we are deriving, or we're subsetting, grid querying out our final metrics for analysis right here. So data derivation from parent data source to our generated rasters from which we can subset out further information. And then later on, once we start pulling this information in to our backwards design, there will be some type of an analysis that occurs here. And that analysis is one that we will want to think about whether or not, in other words, how do we intersect, or how do we evaluate these two raster layers together to give us a suitable prairie habitat. Okay, so we've mapped out our Brian problem. Mapped out our Brian problem from left to right. And I encourage you to do this with all of your problem solving, because it helps you to really frame up the problem, understand the data, seeing how everything connects. This is a more conceptual way of kind of a to Z analysis, and it helps you to identify potential gaps or inconsistencies or even questions that you might have. All right, so I'm going to come back to my Pro session. And in my Pro session, I've already downloaded into my session here the Winona DEM. This is, I think, a 30-meter DEM. It doesn't really matter what the DEM is. This is just for illustrative purposes. You know, if you wanted to use a new 10-meter or 5-meter or 1 foot or whatever it is you want to use, that's up to you. The whole point of it is we need an elevation model to work from in order to help Brian with the problem. With that in mind, let's follow our flow chart. One of the first things that we'd want to do is, remember, we could generate or derive an aspect raster as well as a slope raster. So let's go ahead and do that. I'm going to type in here. Well, I could probably do that in my raster tool. So I'm just going to pause this, pull all that up, and then we'll step you through it. Okay, didn't want to waste a whole lot of your time there on that one, but under toolboxes, so you need to find your geoprocessing tools. You can access that through the analysis tab, or if your setup is like mine, in your rightmost pane here, select the geoprocessing tab. Nevertheless, under toolboxes, similar to what we've been through already, if you want to scroll down and find your spatial analyst tools. Spatial analyst tools. Next, go down to surface tools. We spent some time already in our map algebra. We're not going to go in there quite yet, but now we want to derive data. We want to derive more information off of this DEM, and a way to do that is by accessing this toolbar here, or not toolbar, but toolbox. Now, do any of these tools or functions look familiar? Aspect, slope. Let's go ahead and look at aspect. Okay, so my input raster obviously will be my DEM. Now my output raster, I'm just going to make sure that is being saved to a directory. Now this is just where I happen to be where I'm saving my files. Yours might be a little bit different, and that's okay. Regardless, please remember your path name for this. And I'm noticing right now that I have a folder with a space in here, so that's not really too good. So I'm going to maybe go one level up and drop that file here. So I'm going to call this one aspect. There we go. Again, no spaces. Aspect. Okay, let's run that. Okay, in our coordinate system, it does have a projection. It, meaning the DEM, does have a projection. I believe that's our UTM. So all these coordinates down here with easting and northings and all that, this is really not the actual projection. I think what's kind of troubling is the base map default that comes in when you open up Pro. And so I've deleted those and I just zoomed to my DEM. That's why I arrived where I'm at here. But so don't worry about projection quite so much yet. But now, if we take a look back, so number one, we have our aspect raster. So good work. You've just successfully derived your aspect raster. Good work. Now, let's go ahead and we'll come down and derive this raster from our DEM. So we're right here, right now. That's what we're going to do. All right. We'll come back, scroll down. This one looks like it could do the trick. Let's identify that for slope. Now our input raster, obviously, based on our flow chart, would be our DEM. Our output raster, again, we would want that as our slope. Okay, I'm just going to make sure no spaces. We're looking good there. Output measurement degree, that's what we're interested in here. Percent is different from degree. Sometimes in engineering we're using percent, but most applications that when we're measuring a slope or whatnot will be in degrees. So we'll go ahead and run that. So we are creating a new raster called slope, derived from our DEM. Okay, so here we have our slope as well. Now you can change your values here as well, you know, the symbology if you want to, into a more of a color ramp that's a little more suited for elevation. Like, let's see if we can find one. Yeah, I don't know, maybe something like this. It might look, well, maybe that might not be the best. Something like this, you know, so you can play around with the color scheme for your symbology. Okay, we are now done with our geoprocessing for our slope. Let's come back over. Eventually, we're going to open up here next our raster calculator and under map algebra. Okay. One of the rules, however, going forward, explore your data. We need to explore our data to know what we have. We no longer should really need our DEM, so I'm just going to turn that off and minimize it at the bottom. Now we have our two data layers that we're interested in working with, and I'm going to move my aspect on top and my slope on the bottom. It's just for me, so that when I'm working with my diagram, I like to keep things mentally in check. So aspect layers on the top of my table of contents, and then slope on the bottom. So let's go ahead and subset, or what we'll call grid query out, southwest facing land from our aspect raster. That's what we're up to next. Okay. So in exploring our data, what do you see here that's unique? Explore your table of contents. You know, you can also check your cell size and things like that too. These should all be 30. And there they are, 30. And also the question to ask for yourself is, will this aspect layer have a VAT? Will it have a VAT? In short, if you selected no, congratulations. This is a floating point raster. And what gave that away too would have been these values. Anytime we're creating anything off of elevations, slope, things like that, almost the result will almost always be a floating point. So these will not have any VAT or attribute tables, value attribute tables. Okay, so Southwest. This is really intriguing right here because it gives us the final parameters that we need in order to identify our criteria. So this is I'm going to show you this in a minute here, but 202.5 and 247.5. Okay. So what I was writing down were the final criteria. So if I'm subsetting out all southwest facing land from my aspect raster, I need to subset out values of 202.5 with the range here, 202.5 all the way up to 247.5. Those are the range of values I need to extract from my aspect raster to bring it over into my final, I'll call it my final raster layer. So that final raster layer will inevitably contain values. Well, I'm going to call them ones and zero. Ones and zeros are what I like to use for final criteria because it gives us either yes, it's true, or no, it is not true. Meaning the values that'll be present will be either of this range or they will not be. So the true values will be 1 and the false values will be 0. The same thing will actually be applied to our slope as well of 1s and 0, whereby we'll query out 26 to 50 degrees. Okay, let's come back to our session. Let's go ahead and do that. So we know that we're after over here, 202.5 to 247.5. Go ahead and open up your raster calculator if that is not already up there for you. So we'll step you through this process, and also I will put the syntax and make that available for you in a little solution guide for this week as well. Otherwise, you can simply obtain them from our session right here. Okay, let's go ahead and try use of our condition statement. There are a number of ways to do this. I like the con statement because it gives us greater parameters of control. Now you'll notice that in some of the other exercises that you may have gone through, you can more easily, kind of click on a raster and say greater than or equal than, 202.5 and 247.5 or whatnot, and get the same result. And that's true. Although I'm teaching you the condition statement to really think through the steps that you're doing. Sometimes in the really quick versions of Raster Calculator, you can kind of just click on things really fast and move through them, and you're getting data, but you don't really, well, you may not always know what the data results truly mean. So the con really forces us to stay true to that and work through those. Okay, so with that, I'm going to establish my order of operations here with some parentheses. But I'm going to say aspect. Okay, there we go. And we'll have to back up here a bit. Okay, so aspect is greater than or equal to greater than, or actually I'm going to pause this and I'll pull up the solution guide to show you where that is so you can see what this essentially looks like. But we're going to punch in our parameters here. Okay, I pulled up our word solution guide so that you can see some of the syntax, and this is made available for you this week. And here what we're doing is, I thought it might be helpful to see this before we start coding it out so that you know a little bit more about what it is we're doing and why, to talk through it. So we're creating an aspect final. This is part of our final criteria, a raster that we're creating in our document right over here. This is our aspect final that we're creating, extracting out those southwest facing slopes, such that on the condition where our aspect grid is greater than or equal to 202.5 and where the aspect grid is less than or equal to 247.5. So this is the range. We're pulling values both greater than 202.5 and less than 247.5, where those cells are true. In other words, where they fit within that range, we will write out all values in the new grid or raster to values of 1. In other words, that met this criteria. If there are any values or any cells out there that were outside of this range, like at 200 or lower, or 202.4 or lower, and above this value, then those will be written to false or 0. So in the end, we'll have an aspect final raster containing 1s and 0s. One where this range is true, the other where it is not. So let's go ahead and write. Actually, I wonder if I can just copy this and drop it in. Well, I'll copy it and then we'll try typing it out here too. Okay. And then we said, and you kind of make sure you check your spacing. So we have a parenthesis here before aspect, where it's greater than this value, and parenthesis and. Now we'll bring in aspect again. And you may want to copy this out. It's a little bit faster. And make sure your greater than or equal to signs are correct. And we said 247.5. So if we think through this now, we have on the condition, again, I have an extra space there, so we want to check that. On the condition where aspect is greater than 202.5 and where aspect is less than or equal to 247.5, write those values to a 1. Where it's not true, write a 0. Now we'll save this in our working directory, and I will call this aspect final. Okay, that's looking good. Let's go ahead and try to run this. I think all of our syntax looks correct. And parentheses, 1 at the beginning, 1 at the end, should be good. Okay. I'm going to turn off my aspect and minimize my slope. So right now, actually I don't need my aspect anymore, so I'm going to move that lower. So we just created right here our southwest facing final criteria here in terms of 1s and 0s, true and false values of all land that falls within these parameters. So those are 1s. Let's go down below it now and we'll create, or we'll subset or grid query out of our slope raster this range as well. So kind of repeating the same thing, but just with these numbers. Let's try it. Okay, so I'm just going to turn off my aspect, my final aspect, and let's go into our slope. Basically be the same thing. So if you have your code in there, you could essentially, copy that over again, but this is what that will look like. Final slope, greater than or equal to 26, and the slope less than or equal to 50. Where those are true, write a 1. Where it is not true, write a 0. I'll copy this and paste that in. Okay. Except we do not need the name of the raster at the beginning here. We just need the condition where slope is greater than or equal to 26 and where slope is less than or equal to 50, where it's true, write a 1, where it's not, write a 0. And we'll call this one slope final. Okay, let's run it. All the syntax looks good here, the parentheses. Okay. Very good. Now over my table of contents, I'm going to minimize or actually close out all my original data. And here we are right now. We have our southwest facing land done. That's a check. We have our final slope raster here as well. That is done. So check. Both of these are ones and zeros. Now comes the time where we're really thinking about, like we talked about earlier, the analysis. What do we want that to be? Now, when they're in Brian's original document, he asked in here that prairies around here, it's sort of implied that they're found on both of these. So something that's relatively steep and facing this direction. So we really need both of them in order to be true. So we need both steep and both southwest facing. So that means we have a couple of different options. You know, we're thinking of analysis right here. Really two modes of thought. Binary, which means it's either yes or no, 1 or 0. And in our case here, we really need those to be both the same in order for it to fit. Now, if we were thinking of more suitability, you know, binary versus suitability, where suitability is going to be almost like a ranked system, where we can think of binary, where we multiply the values of each one of these rasters. We multiply them. 1 times 1 is 1, or 1 times 0 is 0, and 0 times 0 is, well, just nothing. So multiplying is probably what we want to do. So multiplication is a good operator to use when we're looking for a one-to-one relationship where it needs to meet all criteria or nothing, where it's all or nothing. Versus suitability, we could think of by adding values. So if we had 3, 4, 5 different final raster layers here to work with, and we wanted to identify what were the more suitable areas, you know, that had a ranking system, like suitability sort of implies a ranking design, a rank. So if you had to allocate resources to potentially high suitable areas, you could do that versus an area where it's not going to be as suited for your needs. So, you know, if you add 1 plus 1, you could have 2. But if you added 1 plus 0, that'll be 1, and a 0 plus 0 is 0. So in our case here, if you were to rank this out, you would see ranges from 2, 1, and 0 because of the adding. So obviously 2s are optimal, 1s are, you know, met one of the criteria, you know, one of the other, and 0 didn't meet any of these criteria. Versus the binary approach, you're going to have either, you know, 1 or 0. You know, 1 times 1 is 1, 1 times 0 is 0, and so forth. So binary is all or nothing. Suitability is kind of a ranked design, if you will, based on numeric value. But again, meaning, what do those numbers mean? I always want to keep track of that. So let's come back over here and we'll try that. So right here, we have 1s and 0s. And for fun, I'm just going to see if I can block out or make no color for my 0 values. So I'm just, in each one of my final rasters, I'm taking the 0s, and I'm just going to come over here to my symbology and just hollow those out. In other words, just put a no color in there. And the reason I'm doing this is so I can show you what's happening if I turn these on and off. So like for instance, if you look right here, you're seeing a couple of cells that do overlap. A few instances where they do, and quite a few where they do not as well. So what we are trying to take out of this analysis are where these cells are all overlapping. that is the goal for us. So all or nothing. All right, let's come back out. And again, we're almost there to help Brian. So congratulations, we're almost there. Let's come back over to our raster calculator session again. And so if you're thinking about this binary type of analysis, ones and zeros, when we think through how that would be to multiply those together to get those cells of commonality, we want where there is overlap. And I suppose in a conceptual way, if I were to write that out here for you, just write this out so you can see that. Sometimes it's helpful to have these cells as we're talking about what are we doing when we're doing a multiplication or a binary type of analysis. So if we're multiplying these, let's say we have our two rasters in here, our aspect final and our slope final. And we analyze these. This is kind of the last step in our approach here for the Brian problem. Just as a little sidebar there, this is called again, a per cell analysis, cell by cell, where the cell is directly in the same spatial overlay as the one beneath it. So this type of a thing. So overlay, that's what we're after. Like that. All right, so if we take 1 times 1, we know that the resulting per cell analysis would be 1 here, 0 and 1, 0 and 1, and then 1 times 1. So what this is telling us is that the ones meet our suitable prairie habitat requirements. Now, if you were to, let's say, add these, let's say if we just did an addition and we dropped that right below, but same layers, just we're going to add them. 1 plus 1 is 2, 0 and 1, 1 and 2. So it's showing us here that the 2s are going to be more suitable than the 1s. The 1s met one of the criterion, but it wasn't as good as the 2. So that's some similarities of this, what we'll call ranked suitability approach versus more the binary or kind of meets all or nothing approach. So some things to think about on that side of the coin. So let's go ahead and we'll come back to our Brian problem solution guide so you can see this in a little bit different way. So if we multiply those together, here you'll see our final slope plus our final aspect will give us our result. And then we'll take a look at what I'll call a bypass method that you can do if you're a little bit more, well, I actually, it's really one of the same. These two are, it's not a bypass method. Rather, this is mostly when I say bypass method and some other activities related to this content. We can sort of fast track some of our analysis a little bit more by building a more involved statement, but this is not the case here. So just multiplying these two together, like we just illustrated, will give us the same result. If we took on the condition where our slope final is 1 and where our aspect final is 1, where those are true, write out a 0, and where it's not, write a 0. If we're to look at this in that condition statement. So condition statement of multiplying are, in this case, sort of doing the same thing. On the condition where this is 1 and this is 1, we'll write an output value of 1. And if it doesn't meet 1, then write a 0. That's what that's saying. So in that case, the con is operating really like a binary type of analysis. So either way, whatever you would like to do for this is up to you. But for me, we will just go ahead and multiply these together. So I'm going to go ahead and just type that in there. So this will be Brian problem's final result, which would be for us here, slope final times aspect final in either order. So all we're doing is multiplying those. Let's run it. Okay. Turn off my other layers. And I'm just going to come back over here and I'm going to make my zero value no color. I'll maybe darken this up so we can see that a little bit better. So here's our final results for the Brian problem. And now we could also convert this to area if you wanted. And if you wanted to convert, your 30 times 30 give you 900 meters squared times your count for values of 1 right here, 45,630. You could generate the total area of suitable prairie habitat. Again, at least given those two parameters that we were given there from Brian, you could generate the total area. So if you're doing some grant work, if you're writing a grant and you were able to articulate or identify the number of area, the potential area, you could write a grant based on the total area and how much that would cost to go ahead and rehab or try to, I guess, restore prairie in those areas. So it'd give you, a count of, I guess, a needs assessment, if you will. So it's a good application, kind of a fun and easy one, showing you the overall process again of what does this take? What does it take when you have a goal? Identifying, again, not so much that we have to know the analysis yet, but rather, okay, what are the parameters that are given? What are the criteria? A criteria, I suggest, is really good if you can identify what that is early on, if there's any clues of that. Usually literature is a good means of that, but then we start to work backwards. If we have our criteria, well, where can we derive that from? Okay, well, if we have some raster data layers, well, where can I where can I get those from? And you kind of keep working backwards until you know what your parent data sources are. So the parent data source is the key to this backwards design. If you just started off with a DEM, yeah, I mean, you could figure your way through this, but it's always easier when you have the goal at the end and you work your way backwards for that. So hopefully that gave you some insight on the Brian problem, and I encourage you to try some slight derivations of this of your own. Make up some different values. You could add in here something completely different, too. But practice with these types of things. It's really good to build this overall workflow design, as we'll call this. This is the Brian problem workflow. There we go. If you have any questions, please give me a shout and I'll help you out. Otherwise, we'll see you all again soon.